Good evening, everybody. We are delighted to have you all here for Pi Day 2023 celebration. Joining us today is Professor Ramanujam, a renowned mathematics communicator and educator. His research interests are in mathematical logic and theory of computation and their application to theory of distributed system, game theory and security theory. The interesting repetition made and the emphasis made in the title has already made us curious. Sir, we are happy to hear from you. The stage is all yours.
Thank you. Thank you very much. Thank you all for coming, and it's a pleasure for me to come again to IISER. I feel at home here. Every time I have come, I've found it very warm and enjoyable, and thank you very much for giving me this opportunity. And this was a title, not quite the title, I mean, the title wasn't, but the topic was suggested by Prasanna and co. So I should really say, so the blame is theirs. So, okay. Yeah. So I think there is some confusion about the title, and I thought, okay, I mean, so why should we learn logic and why should we learn logic? And in fact, if you replace it by mathematics, that's something that you hear everywhere, right? I mean, you hear all through school. I mean, why should we learn mathematics? And most importantly, why should I learn mathematics? Somebody can learn, right? And so on, right? Okay. So first, let me thank Prasanna, Padmapriya, and Hirak for the invitation, and very warm invitation, I must say, and for the math group at IISER Pune for the hospitality. Now, I'm going to discuss only ideas and no formal details. I would be happy to get your responses of any kind. And if there is no time, please write to me, jam at IMSC. So I've been at the Institute of Mathematical Sciences for a very long time, and until a couple of years ago. And now I am visiting professor at Azim Premji University in Bangalore. So the IMSC ID works very well, so you can always contact me there. And yeah, so this is going to be, as I said, general ideas. So, and I know that the seats are very comfortable, so sit back, relax, and enjoy. Okay. Okay, so what is logic? Here is Lewis Carroll. I'll just let you read it and enjoy it. Okay. So, well, that's logic. Yeah. There is a slightly different statement about logic which I like, and this is by a very renowned logician, Georg Kreisel, and quoted by Odifredi. It's a collection of essays by Kreisel. There are two volumes. One is about logic and logicians, and the other is about mathematics and mathematicians. Very well worth reading, I would say. And there he says, logic concerns properties which may not be useful when remembered, but extremely harmful when forgotten. I think, to me, that's a very nice description of logic, right? I mean that, when you study logic, not really clear why you want to do all this stuff, right? So it's not particularly great, when you remember it, but yes, when you forget, danger lurks. Okay, so what is logic about? Okay, most elementary thing is, okay, three friends go to a cafe, one of them wants tea, and the other two want coffee, right? Now the waiter comes bearing a tray with 3 cups. So what will the waiter ask? I'm sorry, usually in India, that's how you expect. And, right, you would think that he'd ask who wanted chai, right? Because then you know that the other two want coffee and you do. I mean, it doesn't make sense to ask who all want coffee, right? When you can ask a simpler question like who wanted chai, right? Because that clearly eliminates the possibilities. Well, I would say this seems like logic. Basically, the process of making inferences in whatever context you are dealing with, right? Seems, yeah. Oh yeah, okay, I'll take it up as I go along, okay? So, bear with me. So, how do you answer questions, right? Is this a prime? God knows, huh? Turns out it is. Who's the president of Ivory Coast? Anyone? Now, unless you are into these quizzes and stuff and are a quiz master or something like that, I think the chances that you would know the president of Ivory Coast is pretty small. Happens to be, I don't know, I have to read it and tell you. Okay. What about the name of the Pune Municipal Commissioner? Anyone? Happens to be, again, I mean, this is all Google knowledge. Okay. Does Prasanna know everyone attending this webinar is actually listening? Webinar, I said, sorry, seminar. I'm so used to writing webinars these days. Right? Yeah? He cannot. So, some things you can know, some things you cannot know. Right? Some things you don't know, but can know if you want. Right? So, these are inferences we routinely make. Right? In the first case, when I ask, is this number a prime? Right? You don't know whether that number is a prime or not, but hopefully you have some algorithm that in mind that you know. Somebody, put a gun to your head, you can actually do a sieve or whatever is your favorite algorithm and check for primality. Right? It may take you a long time, but you have a reliable algorithm and you can actually figure out whether it's prime or not. President of Ivory Coast, I don't know. You may not care for it. I mean, I don't see why you should care whether that number is prime any more than knowing the president of Ivory Coast or the name of the, Pune Municipal Commissioner, though it might actually be of more practical relevance to you, right? Now, the point is that when you say you know or you can know or whatever, you have some process in mind. That process you can call computational, inferential, something that you like, but something you have some process in mind. That's the point I'm making. For instance, but in the last one, when I say Prasanna cannot know, what do I mean by that? What is the process of inference there where I can confidently say that, or am I wrong? It gets much more fun if you start thinking about, what I know of what Prasanna knows and so on, right? I mean, I have a secret, I know some secret X. My friend walks in, I don't know whether she knows the secret or not, right? If she does not know, I don't want to tell her, right? Of course, it's a secret, right? But if she does, maybe she knows more about it. This is the essence of all gossip, right? Right? I mean, we do this all the time, right? I would love to know whether you know it already or not. And if you know, I want to, fish and find out more. Now, how should I talk to her? This is really your, everyday compulsions. And this is the tie-up to semantics. I understand that very well, right? So, but the thing is, suppose she does know X. Now, if she is uncertain whether I know X or not, conversation can be quite difficult. Because she's, by symmetry, she's also going through the same line of reasoning. Right? On the other hand, suppose I don't know X, but I know that she knows, right? She has walked in and I know that, most. Now, is there a way I can find out from her without her being aware that I've just found out, right? Now, this is a sort of questions, this is the kind of inference that really interests me because this, I am saying this is a, arises in, let's say, human context or in the context of communications, interactions, all these things, right? And I'm just giving lots of examples of this kind. I mean, there are, of course, other examples. For instance, this is the kind of pattern of reasoning that you find in cryptography and all security, all this kind of stuff. This is the sort of thing that you're interested in. You may not, remember that underlying inference is what I'm talking about. Finally, procedures are different, computations may be different, the mathematical formulation may be different, but finally it's all about I know that you don't know this or I don't know that you know this, etc. So to motivate all these things, let me take a very simple puzzle, right? So I have 3 red hats and this is a very famous one. I have 3 red hats and 2 white hats. Now I pick 3 hats and place on the heads of A, B and C. This is Martin Gardner. Only Europeans would think of going around placing hats on people's heads. Anyway, so each can see the color of others' hats, but not your own, right? There is no mirror in the room or anything, right? Now, I tell them, at least one of you is wearing a red hat. And then I ask people sequentially. After all, I've named them ABC. So I ask A, do you know the color of your hat? And she says, no. Then I ask B the same thing. And he says no as well. Then I ask C the same thing. And she says, yes, I'm wearing a red hat. Can you explain this? Or maybe, yeah? What is the information contained in every sentence here, right? Now, the first I say at least one of you is wearing a red hat, right? That seems like a completely trivial statement. Remember, I started with 3 red hats and 2 white hats. And I have put, it seems like a completely trite remark. Okay, fine. So 0 information content, right? Okay. I don't know, I'm asking you. Fine, let's get past that. I ask A, do you know the color of your own hat? And she says, no. What does that mean? If B and C were both wearing white hats, right? And she has heard me say at least one of you is wearing a red hat, right? So she would know that her own color must be red. So A's statement tells you that B and C can't be wearing both white hats. At least one of them is wearing a red hat. Okay? Now, what is this information? If C was wearing a white hat, right? Remember, B has heard A say this. And B knows that A is an excellent logician after all, right? And therefore, her reasoning must be perfect, right? So he knows that between himself and C, right, at least one red hat is there. Now, if he sees that C was wearing a white hat, he would have immediately said mine is red. And he says, I don't know. So that's enough information for C to conclude that her color is red. Yeah? So this is the reasoning that's going on here. And of course, one can ask, what is the purpose of the first question? And I will leave you to think about it. Wow, something happened here. It's just, yeah. Okay. So, yeah, let me just go over the reasoning once again. So every statement is actually saying something about what people know, right? If I had seen 2 white hats, right? If A had seen, she would have known hers was red. This is exactly the reasoning that I just went through. So, okay. Now, here is a slightly more interesting. By the way, this puzzle that I have just talked about, I advise you to start thinking about all this. What is this 3 red and 2 white and all that? How about some M and K and so on. And much more fun is if there is an infinite line of people standing there and I have some colored hats and I put them, red and white and so on. And maybe you have a visibility, like I can see people ahead of me, but put them in a line and ask. All kinds of variations are there. I tell you that this is a fun puzzle to extend as you like. Anybody interested? I'll tell you more. Okay, here is another puzzle. This is a slightly different flavor. Again, Martin Gardner. I have thought of 2 distinct positive integers, right? 1 less than x less than y. And let's say that the sum is less than 100. So I'm thinking of small numbers, right? And there are 2 people, Miss Product and Mr. Sum. And the following conversation happens. What does it mean? I go and tell Miss Product the product of x and y, right? And I go to Mr. Sum and tell him the sum of x and y. And they know each other's names and, they know that, product has been told the product and sum has been told the sum, etc. But I whisper so that they can't hear. Now Miss Product says, I don't know what x and y are. Mr. Sum says, I knew that you didn't. Miss Product retorts rather, now I know x and y. To which Mr. Sum says, so do I. So find x, y. Yeah? So, you can see that this is much more fun as we are. But it's again about knowing what you know and what you don't know and what the other person knows, etc. Not very different flavor. So what is the information contained in the first statement? I don't know what X and Y are. And who's saying this? Miss Product. So what do you know? I'm sorry? That's true, but tell me more. Of course that's true, but tell me more. Yes? Not a prime? Both cannot be primes, right? If both were primes, unique factorization, she would have immediately known what X and Y, right? If I had told her a product of primes, Miss Product would have known both. Therefore, at least one of them is composite. So that is the information contained in the first statement. The second one is truly deadly, right? It says, I knew that you didn't. What does it mean? Remember that Mr. Sum knows the sum of X and Y. So Mr. Sum says, for all possible ways of partitioning this number, right, there exists at least one which is a composite. It is not possible to, right, partition these numbers such that you get both primes. It's a very powerful statement, okay. Now you have to play around with numbers, right, okay. It's fun. And the third one, what do you think that says? Now I know X and Y. Okay, at this point, I challenge you, really. If without writing quantifiers, tell me how you would think about it. Because the second one rather, says for every way of partitioning the sum, there exists one of them which is a should come on. Yeah. Third one says, now I know. Okay. Now here again it's a quantifier alternation. It's fun. But what is the content of the last statement? So do I. It says that the solution is unique. If there were two possible solutions that fit this, until the last, Mr. Sum cannot be sure which ones. So Martin Gardner is telling you with the last line that there is a solution is unique. So when I say find XY, I'm not, there is in fact a unique solution, find it. Okay, so do this. I assure you it's a matter of like half an hour to 2 hours, some excitement, lots of numbers. And for those who would like to write a program to enumerate and check, I think you can do that. Python program will give you the possibilities in, a fraction of a second. But of course, you would like the program to do this inference. That is much more fun. If you're just using Python to enumerate these things, not that much fun, right? Okay. So my point on this inference that is going on, look at what these statements. Statements are saying nothing about the numbers. There are no primes and there are no composites and there are no quantifier and alternation and whatever, right? It is in the inference that we are doing from these statements are only about I know that you know something, I don't know something. But they're only saying I don't know, right? But there's a lot you can infer. And now, again, there is a slight haze here about is this inference or is this computing? Is this computation? But I would like to claim that it's all the same thing. In fact, that's part of what I want to say. So, questions, right? Now the title. Why should we study logic? Why should we study, when I say logic, I mean mathematical logic, right? Okay. And why should we study mathematical logic? There is philosophical logic, mathematical logic, as people usually distinguish. And logic has been thought about by philosophers for a very long time. In the last century, it was more mathematized, and now you look at it from mathematical means. And the question is, most important question is, why should I study? In fact, I wanted to put I in the title, but then you can't emphasize I, no? As it is, it's difficult enough with the repetition, and poor Prasanna, trying to underline I or something like that. Not possible. So, okay, so that is why the we. But the real question is, why should I bother, right? It's all interesting and important, let somebody else do it, right? This is the typical attitude to mathematics anyway. And of course, there is a most important question is logic helpful in understanding mathematics, understanding nature, understanding society, the world at large? And I would like to, today at least, I've given this talk for math students and for computer science students, and usually I talk there either computation or mathematics. Today I thought I would talk in a general, more general context and society at large, right? So understanding society, how about that? Isn't it much more fun? That's why the kind of examples. So there is this beautiful paper by Eugene Wigner in the 1960s, right? It's called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. I mean, he says, why should nature be like this, right? I mean, you use some very, very simple equations, the Dirac delta function being one of the most beautiful and famous ones in this regard, and then nature seems to follow, right? Why should nature have any of that elegance and any of that, right? So that's a very interesting article. I would strongly recommend that for everybody to read it. So physical theory's mathematical structure often points to further advances, but why? I'm not going to take this up. In fact, logic similarly has pointed the way to computation. And in fact, I would call it the reasonable effectiveness of logic in computing, or, this understanding of inference as computation. So a very brief history of computation is tied to logic, right? Leibniz was interested in building a machine to derive logical relationships. And Boole, the famous book called The Mathematical Analysis of Logic. Then Jevons built logic machines. Peirce, there is a beautiful sentence by Peirce where he says, calculating machines are specialized logical machines. And remember, long before computers existed. And now, what makes mathematics so reliable? Well, in science you talk about experimental verification. In mathematics, it's about proof. Now, proofs the high road to truth, right? There is a book by, sorry, I've forgotten now who, To Truth Through Proof. Try getting your tongue around it, yeah? So that's the slogan, right? So question is, what is a rigorous proof? Now, I just, outside chai, Anisha was telling me about proof and rigor and so on, right? We were just talking about it. It's not an easy thing, right? And in fact, when you learn mathematics, it's very hard to grapple with. When you need proof, often statements look obvious and you're told to prove them, right? So when do you need proof, and what is this, mathematicians are very fond of talking rigorous, which really, zaps you out. What the hell is that? I mean, formal proof, at least I understand. Now you are saying informal but rigorous, right? And so on. In fact, can I mathematically answer this question? Can I mathematically say what is a rigorous proof? In fact, so people thought about it in the last century, and a whole lot of people discussed this. And one good way to answer this, which really goes back to Hilbert, is that, well, if you say a rigorous proof, it should be machine checkable. This is one very, very nice formulation. So, but then what is machine checkable, right? Because what is this machine that you are talking about? What machine? This dabba or that dabba or which? Well, yeah, so same as computable. And this was one of the revelations of the last century. And so, in fact, it's at the heart of mathematics in this sense. Inference and computation are basically very deeply linked. Well, computation and thought. Here we are talking about thinking, right? We were talking about reasoning, inference, mental processes. Is it really possible to do this? Leibniz actually says, Leibniz says, I dream of a future when two people debating sit down and say, okay, enough of argument, let's calculate. So, exactly, okay. And this was a question that drove a remarkable mathematician in 1854. And this is George Boole. And Boole published a range of papers in mathematics, mainly in differential equations, integration and the calculus of variations. He wrote 2 books outside this. One was called The Mathematical Analysis of Logic in 1847, and the second one is really grand, an investigation of the laws of thought on which are founded the mathematical theories of logic and probabilities, 1854. And I mean, what an audacious idea, right? To even think of writing down algebraic equations to describe laws of thought the way we think. How did Boole actually decide to try such a thing? How did he even expect to succeed? What did he actually do? This is one of the important things, that Boole was actually self-taught. Keith Devlin says that it may have been the absence of a teacher to lead him away from such a seemingly nonsensical idea that enabled him to seek to capture the patterns of thought by means of algebra. If he had, heaven forbid that he had had a PhD advisor, right? Advisor would have said, never ever think about problems like this, right? I would be scared of a student wanting to think about algebra of laws of thought, right? So Devlin says it was, Boole was really self-taught in the sense that he was the son of a bookstore owner, bookbinder, and he taught himself all of mathematics, and he never completed school, let alone go to university. And but he was deeply interested in mathematics, and he was discovered, so to speak, by De Morgan, who encouraged him to publish, and so he started working on. By the way, what was called calculus at that time is what we call algebra today, and so anyway, it's all funny stuff. Yeah. So Boole's idea was that you represent by symbols classes, collections, things like that. Importantly, don't worry about whether they exist or not. This is a major departure from Leibniz. And so, for instance, he said, let the symbol 1 represent the universe, which comprehends every conceivable class of objects, whether existing or not. Okay, this is a very grand announcement. And then says, let's just write down some equations about collections, right? And so if X represents Indians and Y represents logicians, Indian logicians is XY, right? Right, XY. And X plus Y is take your class and divide it into 2 parts. And then he quickly gets into a discussion of law, and he says, okay, you wanted this to be Indian logicians are the, well, I don't know, logician Indians, is it the same? But whatever. And you get idempotence for free, and distributivity. So he gets on into this kind of characterization. And in the mathematical analysis of thought, another important thing is that he says not X I can represent by 1 minus X. Remember, 1 represents the whole universe of class, right? And so not X is basically 1 minus X, right? And therefore the power of algebra comes, right? So all X is Y is now represented by XY equals X, right? And therefore Boole concludes that X times 1 minus Y is 0, right? So I don't want to go too much into Boole's book, but basically reasoning by equation. And so this is the fundamental tie-up that I want to, emphasize here. Inference and equational reasoning are not very far, right? Equational reasoning, which lies at the heart of mathematics, is something that is one particular formalization of inference, right? And yeah, Boole was very proud of this method. In fact, the second book, by the way, the second half of Boole's book is almost forgotten, right? Remember that he wanted to apply this thing. So the second part is on probability. And he wanted to talk about fundamental laws that govern society by analyzing large quantities of actual social data. So Boole actually talks about what is very popular today as data science and so on, right? And except that nobody bothered with that part. Second half is pretty much forgotten. And so lots of ways of solving equations. But Boole didn't actually get down to the axiomatic method, which we know of more from the 20th century, right? And he didn't really discuss rules of inference. But importantly, as I said, simply and briefly with remarkably little fanfare, Boole presented a completely new foundation for this algebra of logic, right? And the rule of 0 and 1, right? 0 talking about the empty collection and 1 representing everything, right? And so on. So let me not go into this. So what we call Boolean algebra is a reworking of Boole's ideas by later mathematicians, right? There is a whole lot of stuff on Boolean algebra here, let's skip that. So, Halmos calls Boole one of the most influential mathematicians of all time. And, Halmos wasn't even referring to computers and gates and, communication theory, right? So, the point is that by reducing all reasoning to algebra, Boole opened up this possibility of building a reasoning machine, right? And Jevons actually went on to build such machines. And, okay, let me change track, fast forward, all this, 18th century stuff, right? And 19th century stuff, right? So, in general, it doesn't make any sense to ask, when was molecular biology born, right? What is the birth date? But mathematical logic, I can tell you. So, it is September 7, 1930, Sunday about 3:30 p.m., right? What is this? Okay, this was a conference in Königsberg. It is called some really obscure name, Second Conference on Epistemology of the Exact Sciences, part on Foundations of Mathematics, and there is a panel chaired by Hans Hahn, a reputed mathematician, and the speakers were Carnap, Heiting, von Neumann, Scholz, and Reidemeister, all mathematicians who contributed greatly to many, many different areas at the time. And they were all talking about how, different ways of foundations of mathematics can be reconciled. And one young bespectacled man got up and said, this all looks very good, but actually I'm not sure you can do it, etc., etc. And, and typically in seminars, somebody always asks a question like that and the session chair says, oh, that's very interesting, we'll think about it. And that's it, right? That's all that happened to this person as well. And then everybody said what you always do in conferences, we need more conferences, and when do we schedule the next conference, and so on. And the thing ended. But von Neumann was sufficiently bothered by what he heard, and I think he was the only one who was really bothered. So he buttonholed this chap at dinner and asked, what were you talking about? And this was this man who tried to explain to him what he was thinking. And von Neumann says that he realized that if what this man was saying was true, it was going to be terrible. That all that stuff that he had been building was going to be wrong. And being von Neumann, he was on a ship going from Europe to the US, and I think he pretty much worked out the proof on his own. But then he wrote to Hans Hahn, who was the session chair and who was in fact the advisor of Gödel, to talk about it. Those days that was the idea. You do your work and then the advisor goes and gives the talk. So Hans Hahn presented it in Vienna, and then it's all history about it. So this was basically what was called the Hilbert's program, if you've heard of it. It says basically, you take a sentence, and one of the problems, Hilbert's problems, was this thing to ask, I just write some sentence, for all x there exists y such that something happens, etc., right? Is there a model, in the sense that is there some mathematical structure that makes it true or not, right? Seems like a very algorithmic question to ask. And Hilbert believed that it's a matter of finding a procedure. And he said, yeah, it's a matter of finding the procedure, and you will know a procedure when you see it, right? So you don't need to define any such thing, right? I mean, people have been solving equations for centuries. Nobody bothers to write and say, what is a procedure for solving equations? You don't define it, right? And this is David Hilbert, and here is his famous slogan. In fact, I can play the radio recording from Deutsche Radio for you if you care. Where he says, wir müssen wissen, wir werden wissen. We must know, we will know. The point is that once you formulate it mathematically, a question has a very precise answer. It may be difficult for you to find out, but that's an open problem. We'll all start working towards, right? And yeah, this is interestingly same day in Königsberg, same city where Hilbert was being felicitated on the day of his retirement. Okay, so that's why I said, yeah. So Hilbert's program was, so what I was talking about was this connection between mathematics, formalization in mathematics, and reasoning, right? Hilbert wanted to simply formalize what I was talking about. Formalize all mathematics into some axiomatic form, so that any mathematics you do, whatever computation you do, whatever derivation you do, whatever, all of it is inference of some kind. It's inference in some axiomatic system. Write down the axioms. It's a matter of finding it. Write the axioms for arithmetic, for geometry. Algebra, of course, is axiomatic, no question, right? And so on. But then so also quantum mechanics, right? Why not? And so on, right? So anything that you mathematize, you axiomatize. That is the slogan. And then, of course, a proof that all this axiomatization is consistent, right? Because it should not be inconsistent. Now, one important criterion that he said was, anything you call a proof should be finite length, should use only finite resources, right? So that I can communicate a proof to somebody else. And so this is the slogan. And a priori, it's very reasonable. And basically, Gödel comprehensively destroyed the Hilbert program. He showed that any formal system, if it contains some reasonable fragment of arithmetic, addition and multiplication will do. Primes will do. That's all. We'll have some sentences that can always be, that can neither be proved nor disproved. So there will be true sentences, true mathematical sentences, not derivable, therefore incomplete. He also showed that if it's true, you can always add it as an axiom. But if you add it as an axiom, there will be another sentence waiting for you, right? So it's inherent incompleteness, and it goes all the way. In fact, he also suggested, he didn't prove it, people proved it later, and any system that can prove its own consistency must be incomplete. This is also a, death blow to Hilbert, because, in mathematics, you want to prove consistency by mathematical methods, right? So you would like to prove for a system that proves its own consistency. And, well, let me skip this. It's not that important. I just wanted to say that von Neumann used actually Gödel's proof technique to build the model of a modern digital computer, which we call von Neumann architecture today. And here is von Neumann. Yeah, so Gödel's work still left this question open. Because if I write some sentences in logic and ask, does it have a model? Is there a structure that makes it true or not? Who says it must be, your effective procedure, is there an effective procedure? Well, there may be one, because it could well say yes, no, and then say I don't know, right? There may be some sentences, right, for which both it says I don't know any proof, right? And so basically after Gödel, people didn't expect positive result. To show that, but there is a big barrier to answering the question, and that was, see, if there is a procedure, I can just give you the procedure. To show there is no procedure, I must define a procedure, right? How do I say that there is no procedure without, how do I prove that there is no procedure without actually defining a procedure? And that should be defined mathematically. And then you get into the same chakkar that Gödel is warning you about. So what do? And this was what Alan Turing, this British mathematician who solved the Enigma code famously and therefore became a film star, right? And so, he wrote a single paper in 1936, and it's a remarkable paper because in one paper he managed to do all these things. He defined the notion of effective procedure, showed that it can simulate any physically realizable notion of computation, and hence as good as any intuitive computing machine. He showed that it has limitations. In particular, it can't solve the problem in logic that we talked about, that there is no procedure to take a sentence in logic and check whether there is a structure for it or not. And he in fact did one better. He showed that there is a universal machine that can take any other machine as input and behave like it. thereby starting off operating systems and compilers and so on, and modern computing as we know. Right? Okay. So let me not go into this. What's happening? This thing doesn't like. Yeah. So okay, all this stuff is history, right? So what? Right? History is all okay, but why is it relevant today, tomorrow? Why should I worry about it? For instance, does society need mathematical logic? Right? Is it just something that mathematicians are having fun with? And, one good answer for this is that logic helps to make the familiar unfamiliar. And in this process, you get new perspectives, right? And I'm going to give one example. There are like lots and lots of examples from different disciplines. So for instance, the good old number line, right? The set of natural numbers with the standard ordering on it. 2 is less than 5. 5 is less than 72. 72 is less than 1784 and so on, right? So the number line. Now how well do we really understand it? What are its properties? Can I define the number line entirely by its properties? That would be, then only you can say you understand it, right? Well, this is something that people thought about. Dedekind had some nice formulation, Peano formalized it further, and basically there are only a few properties. 0 is a natural number. You take any natural number, it has a successor. If two numbers have the same successor, they better be the same. The successor function is injective. There is no natural number whose successor is 0. And then one thing that we all learn about natural numbers is the principle of mathematical induction, which characterizes the set of, if a property holds for 0, and whenever it holds for some number m, it holds for the successor of m, then it holds for all numbers, right? So this should suffice to characterize the set of natural numbers, and this is what Peano proposed. But do they? Is there any hidden property? I mean, today there was this brilliant exposition by Tejas on Platonic solids, and he gave a beautiful proof for there are only 5 Platonic solids. And afterwards, when we were coming out for lunch, one of the students came out and asked, okay, he had written many equations, right? V minus E plus F equal to 2, relation between degree and number of vertices, degree and number of phases, etc., and then used equational reasoning to finally show, inequational reasoning as well, to finally show that there are only 5 Platonic solids. But then one of the kids came and asked, but you use some equations, but what if there are more equations, right? And yeah, but the thing is that, well, these equations suffice to show the proof, but maybe other equations, and the point is that what the student was asking was that, okay, what if there are new equations that contradict this somehow, right? So how do we know that these properties, these axioms suffice, right? So it's a brilliant logical question. It turns out, of course, the number line studies these, satisfies these axioms for sure. But then there are also other structures. You take the number line, put a point at infinity, right? Well, that one has to have a successor. Let me call it star. Star plus 1, star plus 2, star plus 3, right? Above the number line, right? Point at infinity, and after that its successor and so on. This is a mathematical structure with an ordering on it. So we have a structure with 2 copies of the number line, one sitting on top of the other, and that satisfies the axioms as well. Now it doesn't take much to see that if you can have 2 copies, you can have 3 copies. Surely you can have countably many copies. How much can you go? There are bizarre creatures waiting for you out there, right? These are what are called non-standard models of arithmetic. A very nice book by, several people, but let me skip that. In fact, there is a very nice theorem in logic that says there is no countable categorical description of the set of natural numbers, right? What do I mean by a categorical description? If I can write down some axioms and then I can show that any 2 countable models of these axioms are isomorphic, then I will call it categorical, right? Then only I have described the natural numbers up to isomorphism. Then I can say I have defined it. Theorem says there isn't any such, at least in first order descriptions. Okay? So, I mean, that is the technical part, but let me skip that. My point is that mathematical logic, what did I say? It helps you to make the familiar unfamiliar. The good old number line, you start looking at it. On the other hand, another lecture, and you realize that the rationals, there are countably categorical descriptions of the set of rationals. I can give you some axioms and prove that any two countable models of the set of rationals must be isomorphic. So what is going on? Well, one is discrete and the other is dense. That is the clue, right? But how far do you go? Of course, for the reals, completion, ordered fields, I hope people remember some things, okay? So all sorts of stuff starts happening. But let me not get into these things. I told you about, you have some algorithms, procedures in mind and interaction, and I'm talking about exotic, esoteric stuff, right? Let's get back to normal social behavior, right? Now, one thing let me just say, anybody who has written a program knows that it's always buggy, right? Full of bugs, all kind, first compiler error, getting past that damn compiler error is hard enough, and then you produce an output you feel greatly accomplished. And then you realize that the output is all wrong, right? And so, is it only a matter of documentation? Well, you would actually like to develop programs with some formal proof of their correctness, right? Ideally, my compiler should give a proof that my program is correct, right? Compiler should certify not only no errors, it should say, hey, here is a proof. That would be great. Unfortunately, there is no such program. We can prove that there is no such program. But anyway, logic is helpful and this is fairly straightforward. Let me get to society. Society depends on many procedures, providing infrastructure, holding elections, distributing vaccines. Now, their functions depend on assumptions about implementation mechanisms, also about people's behavior. And this is the connection with what I started with, I know that you know, etc. Right? In fact, social algorithms have an underlying logical structure, and you can study it logically. And it can help you solve social problems by teasing out hidden assumptions and pointing out inconsistencies. And let me just take one example. Okay, first, what do we mean by logical properties? Logical structure, right? Take a key, house key, right? When I buy a house and get a key to it, the key signifies two things. One is enabling and right of possession, in the sense that if I have the key, I can enter the house, right? And I have a right to enter. A thief who steals the key is enabled, can enter the house but has no right, right? And once I have lost the key, I have lost the ability to enter. So I am not enabled, but I still have right of possession. Now, a login password is like a key because, right? Hopefully, a login password lets you enter your account, look at your inbox, right? And you have a right to look at that. But does it have the same properties? Is there a, description up to isomorphism that I can think of? That's fun. I'm not going to go down that. For instance, security of various kinds illustrate many such things, okay? Secrecy says what is meant for me should not be seen by somebody else. Privacy, many people confuse these two. These two are very different things. I have some notebook on my desk, right? You have no business looking at it. There are no secrets there, it's just my notes, right? Privacy means that there's no secrecy violation when you look at it, but there is a privacy violation if you look at it without my consent, right? This is how we talk about it, and so on. And authentication, and a whole lot of such things. What we would like is actually a proof, right? I mean, why do you lock your door? Because it gives you a sense of security, right? If that key was Xeroxable down in somewhere in Pune and everybody has a copy of that, you wouldn't feel very secure when you lock, right? Because the key is like your certificate of a proof of security, right? So you would like a proof, and the very word proof tells you that there is logic involved. Let me, that is only as an example. But very often, even if you have a procedure or inference procedure, it's not just about how you do it, but even why it should be implemented at all. Okay, here is an example. Two-horse race. right? Winner gets a prize. I mean, both the jockeys are trained to ride fast. They ride hell for leather. Whoever comes first wins. No problem, right? Now there's a slight twist. I go and tell them, we'll run the same race, but the slower horse will win the prize. Right? How would the jockeys run? They both look at each other and say, you start. The guy says, no, you start. Both are very courteous, but will they start at all? Why would you do this? So what is the solution here? Yeah, switch horses. Right? I ride your horse, you ride my horse. And we are trained to, ride hellfire leather. We both this thing. And whichever is, remember, the slower horse wins. Right? So the point is that it is not about the existence of a computation or a procedure or an algorithm to solve the problem. It's about how you use it where. Right? Okay, let me take this example of voting. Right? Well, here is from Bihar elections from 2 years ago. Or whenever it was. So, mechanisms for implementing elections, you would think are very important in a democracy, right? But what logical properties do we expect of this procedure, right? Certainly eligibility of voters, right? Only eligible voters should vote. This is not obvious, for people in this generation. You may not realize that booth capturing was one huge issue in India, right? All kinds of people would be casting votes and who don't exist at all, right? So all this has been, but nowadays that's not a big problem. Confidentiality of votes. I mean, Indian elections, for all their chaos, have been remarkably successful in this, that votes are actually confidential. Anything more? Anything else? Yes? One person should not be able to vote more than once. Only once. Very good. Any more? Actually, if you start thinking about it, you start really, if you think of a theory of elections in this sense, lots of possibilities. For instance, we should be able to check that every cast vote has been counted. This is very important, right? Suppose otherwise one whole booth, right? The cast votes are, one voting machine was simply not considered. It's a disaster, right? So, even better, in a democracy, I should be able to ask, has my vote been counted? Right? This is a constitutional guarantee that you have a right to vote. This is franchise. So, this is a property that I would say it's important for a democracy. Partial results should not be available until all voters have voted. Remember, in India now we have 8-phase elections, 6-phase elections, depending on, certain people whether they can travel or not, right? So, I don't know how many phase elections you will have. And point is, if at the end of the 3rd phase you are getting a pretty good idea of how the election has gone in the first 3 phases, of course it will influence the 4th phase. But this is one I like very much. This property. No voter should be able to prove to another how he or she voted. Right? Suppose it's possible after the election that I can come and prove to Prasanna that I voted for DMK or whatever. Right? What does this open up? One is bribery. Right? You can say that you show that you voted for me, I'll give you 1,000 rupees. This is a benign version. What is the malicious version? Prove to me you voted for me or I'll break your legs. Both are possible in India, right? So you would think that this is a very important property that you would. Question is there anything more? And now comes the important question for me. Can we even prove that all these requirements are logically consistent? Right? Alternatively, can I show that there exists an election procedure in which all these properties can be guaranteed? My point is that you can start thinking in such terms, right? And then there is a surprise. We have a theorem which says that there is no election procedure that guarantees all these properties together. Maybe not that surprising to you, but well, it requires some formalization, it requires some proof. In fact, there is another theorem which says that if we give up either universal verifiability or individual verifiability, then there exists procedures that achieve all the rest. Now, I'm only saying they exist. That's very different from actually, democracies working with. And my point is that mathematically, you can show that, there are choices to make. And then, of course, as a democracy, you should choose what is yours, etc., etc. Right? My point is that logic can help look at, when you think of structures purely in terms of their properties, definable in some particular fashion, then you can start asking these questions and prove theorems of this kind. And this is something that my former students and I proved. So this is something that we can do, right? So it just opens up ways of thinking. That's the main point I wanted to make. And of course, these. Another one is logic for law. Rights and duties have inherent conflicts, right? And they need to be resolved procedurally. This is the essence of law, right? Law is all about procedure, right? And procedural violation is taken very, very seriously in law. But now comes the question. Well, for instance, the clash between the right to free speech and the right not to be insulted. Big deal in India today, right? Now, question is, suppose there is an existing legal framework and I want to introduce a new law. How do I make sure that, see, obviously why did you bring in a new law? Because you had a problem with the old laws, right? Therefore, you're bringing in a new law. How are you sure that the new law is going to be consistent with everything else, right? So this is a fundamental logical problem, right? And you can ask these questions, and formalization is very important. And okay, I'm going to skip a whole lot of it, it's almost time. So let me skip all this stuff. I'm sorry, these are nice examples, but let me skip. Silk board for anybody who knows Bangalore. Yeah. So is there some pattern of reasoning for society as a whole? And my claim is that such logics make sense, right? It's not that these are, conclusive answers, but the point is that you can think in such terms, you can mathematize. And so main point is that you can look for a logical framework for social procedures. What do you want from them? Well, you should be able to detect inconsistencies. This is the fundamental role of a logician in looking at anything. We should be able to calculate consequences of modifying assumptions. You change something, you change one axiom, right? How do your structures change? And we should be able to, of course, this is the particular to society, with something like individual rationale to social rationale, which is what all those examples were about. And okay, let me also skip all this stuff. Let me mention this. This is this Aadhaar card that you all have, right? Digital IDs. In 2017, World Bank put out a statement called Principles of Identification for Sustainable Development, right? Very recently. And it gives some 10 principles: inclusion, design, governance, and so on. And they roughly pertain to digital IDs like Aadhaar from the viewpoint of the citizen, the technologist, and the government. And when we spell out these, now the point is, I went through this document, right? It's a 200-page document. You go through these requirements, it's quite unclear whether they are consistent. In fact, I would stick out my neck and conjecture that it is inconsistent. It's a matter of finding out the inconsistency, right? There's a dire need for formal logic here. And remember that something like 300 countries today have gone for national digital IDs, right? And for a whole lot of African countries, it's all guys sitting in Pune and Mumbai and India IT crowd who are sitting and implementing those algorithms for many African countries. TCS is one of the big ones doing this. Who knows what these algorithms are doing, right? So, do you know the algorithms that underlie Aadhaar, right? So, my point is that the requirements of these things, how they are spelled out, okay, there is a lot of work out here. So, my point is only that here my point is only that logic is useful, helpful about thinking about many things. And I chose to take up a couple of examples from mathematics and social procedures to illustrate this, but you can generalize this to many. And people have done that. It's not, okay. So let me also skip this. So here is a beautiful book by Cathy O'Neill called Weapons of Math Destruction. And she says how big data increases inequality and threatens democracies. I would, so point is that algorithms are weaving into our lives, right? And you use words like my inbox folder, much like my pen, but they have very different logical properties actually. And we speak of my community and my identity, and these are very different in physical and digital worlds. And today, as these worlds interweave much more, you have, very important social questions to understand. The analogy is to food. From the days when we got food directly from farms to how you do, and not only supermarkets but Swiggy and so on, right? The distance to food, as it increases, you can't stick to experiential understanding, right? Formal understanding based on properties is what we are talking about, right? So back to the question, why should we study logic? Logic is unlikely to help anyone become cleverer. I'm a good example of that, right? I mean, I'm not smart and I'm not clever, and I don't think logic helps anyone, become clever and smart. But it is indispensable for understanding. Remember Kreisel's warning? It's not the sort of thing it helps if you know it, but if you forget, you are, it can be dangerous, right? It helps in disciplining thought, becoming aware of hidden assumptions, detecting inconsistencies. And it's for those who like to dig deep, who seek foundations of any discipline of thought, of any matter of practice. And most importantly, of course, logic is fun. So let me end with another puzzle. Okay, there are 7 cards, numbered 1 to 7 or 0 to 6, as you like. Let's say 1 to 7. And there are 3 players, A, B, and C. And I deal 3 cards to A, 3 cards to B, and the remaining card to C. Okay? The situation clear? 3 cards to A, 3 cards to B, and the 7th card to C. Now, I want something that A says, something that B says, something that C says, and everything is said in public. No whispering, no private stuff. Whatever A says is heard by both B and C, whatever, and so on. Right? So, any number of communications. At the end of which, A should know all of B's cards, B should know all of A's cards, but C should be uncertain about all the 6 cards. Remember, C has 1 card and doesn't know about 6 cards, right? So at the end of which, C should be completely uncertain about all the 6 cards, whether they are with A or B, right? But A should know all of B's cards and B should know all of A's cards. Yeah. And don't get into cryptography. This is more fun thinking about it. For those who like to think of homomorphisms, it's a nice clue there. But whatever. It's a nice puzzle to think of. I just wanted to end with saying the logic is important reason why we should study logic is that it's fun. Okay, let me end with one more quote, and this is a famous one that we have all probably learned in school. Rabindranath Tagore, where he says, where the clear stream of reason has not lost its way into the dreary desert sand of dead habit. I mean, you couldn't rub it in more, I think, than how Tagore said. Right? So probably that is, I would say that when I talk about teasing out hidden assumptions, that's what Tagore is talking about, right? The dreary sand of dead habit, right? By just habituation, you get used to things, you take things for granted. Reasoning is about, digging all that assumption digging, right? Okay, thank you.